So Crank-Nicholson, like I said, is kind of the last of, I don't know what the right word is for it, but it's like a conventional technique. It's a technique where you are controlling the time step that's being taken, and you're controlling the way that you step forward, right? There are other techniques that are really powerful, but they are sort of more algorithmic in nature. So there's two implementations I'll talk about. One is in Ease and one is in Python. So in Ease, you can use something that's called the integral command. And the integral command just says, give me a sum state equation. I don't care what the state equation is, just give me a state equation. If I give that state equation the current temperature and the current time step, this algorithm will figure out how and to what magnitude to step forward in time. So it's basically taking your function and it's integrating forward in time using this integral function that's shown here. So you have your temperature, you provide an initial temperature, some initial condition, and then it's going to evaluate temperature by taking the integral from 0 to tsim, the simulation time window, by evaluating your state equation here. So in Ease, it looks like this, where you say the function should be something you want to compute, some initial condition, plus the thing that you're integrating, and that's the integrand, so that would be like an expression. The integration variable here, which would be temperature. This would be integration variable is time. Get that right. Integration variable is time. Lower limit is the lower limit on time. Upper limit is the upper limit on time. And then you can force a step size if you want, but that's really the point of this, is to automatically compute step sizes. So then for our example, it would be like this, where you'd say temperature equals initial temperature plus the integral of dt dt. This is, again, some expression that you put in with the limits given. I guess we could look at that. Oh, I don't think I opened that one. The same thing, let's not look at it in Ease. I think you'll see what happens in Python is very similar. But this is how you do it in Ease, okay? And Ease will happily march through and solve for your temperature. A similar thing can be done in Python. In Python, you can use something called an ODE solver. It's really the same idea. You are defining a function. So up here, we've defined some dt/dt function, a state equation. You give to that state equation time and temperature at the current moment, in time. And then the job of this function is to return the calculated gradient. So you have to define this, right? This is your job. As long as you get this far, that's it. You're pretty much done. Then it's just implementing it. So again, it integrates forward in time. The one that I found works pretty well is in the SciPy library called Solve Initial Value Problem, Solve IVP. There's an analog for this in MATLAB. I think it's almost the same function name. Again, you're giving it the function name that you've programmed here for your state equation. You can optionally give it a time span, an initial temperature, and then some tolerances that need to be solved. Here's some common tolerances. So, RTOL is the relative tolerance for the solution. Absolute, so that would be like, you want it to change by 0.001 of whatever the magnitude of the current temperature is, right? That would be the relative. Absolute would be the temperature value itself. So not like a fraction of temperature, but the temperature value itself. The initial step size, maximum step size, and then args is important because if you have something going into this dt/dt function that's not time or temperature, you need to pass that those arguments here through this function here. So you'd say all this stuff and then args equals, h bar or conductivity or whatever the parameters are that need to go into here. Okay? So let's look at how this is implemented. First, any questions on this? Okay, it's a lot of words, but I think it just helps to look at how it's implemented. All right, so we're down here. So our method is ODE in this example file. So we scroll down here, and in this ODE method, what you'll see is, first, let's look at this here. We have solve IVP. Solve IVP is being pulled from, if you look at our imports, it's from scipy.integrate. So that's a function in that library. So down here we have solve IVP, dtemperature, dtime, the time bracket that we want to evaluate this over, so 0 to tsim, and then we give it our initial condition here. So this dt is a function. If I wanted to, I could define this as its own function here, this, right? So I would say define a function that takes in time, temperature, other arguments, and then it returns the evaluation of my state equation. So it's a little hard to see, but it's T infinity minus T over tau, right? That's our example that we're working with here. So it's evaluating dt, our state equation here. I would then pass the name of this to this argument here. Another way of doing the same thing for a really simple function is to use the lambda operator in Python. So this is a little confusing, but it's basically a shorthand way of writing a function. So you say the name of the function equals this keyword lambda, and then after lambda you have the arguments for the function, time, temperature, and then the thing that the function has to return. So if you want to just do this in a really compact way, it's a really simple function. You could do it like this. Then you just take this dt, plug it in here. If you wanted to evaluate this anywhere else, you just call it like a regular function, right? The other thing you could do, which I didn't, was you could just take this part, the lambda, and the lambda on, and drop that right in here, right? So you're kind of programming the function right into that place. But it's just a Python thing that you can do. So the result that comes back gives you what? So it gives you some object that has properties. And the Python properties that we care about are something called, whatever the result is called, .t. So that gives us our first thing back, or the place where it's evaluating or the time steps where it's evaluating the temperature. And then we want the temperature, which is the result .y0. So this is just, if you look at the documentation for solve IVP, it'll tell you, I'm going to return to you this thing, and it's got this member y, and it's the first thing in there. So you can just sort of copy this, or you can look at the documentation for how that works. OK, so that's the implementation. If we run it, you should see something maybe interesting. OK, so interesting, right? But if you look at it, the green line again is our analytical solution. Red dots are where it's evaluating the time, res.t. So it has decided that it can get a perfectly accurate, or within your tolerance, accurate answer by taking 5 time steps over this entire horizon. With the goal of this is to get the accurate temperature at the end of the time horizon. So it doesn't care that it only had to take 4 and it's kind of weird looking inside the problem. We're only concerned with being accurate at the end. Or this integration technique is only concerned with that. So we, wanting to know what the actual temperature profile is, might want to go back and change this a little bit. But it's kind of interesting to realize that by doing this numerical integration, it can get a really accurate answer this way. The more complicated your problem is, the more stuff that's going on in the forcing functions, the more nodes it's going to need to take. But this is just one way of kind of representing what it's doing internally. Yeah.
What's the black line again?
That's our ambient temperature. So that's the thing that's changing with the condition that's changing. So this is probably, if you handed this in your homework, I might give you some sideways look on that. So let's look at how you want to improve this. So you can go back here, and we can add in some other optional arguments. So let's say I want my maximum step to be some value. You can use this argument called max step. Let's go back to our 11 nodes that we had before. And now you can see that it's giving you a more reasonable result. But I guess one thing to point out, you've got even steps here in the middle. But this algorithm is calculating the step that's needed, to maintain accuracy. So right at the beginning, it's decided it needs to take a really short step to maintain accuracy. So it does that, and then it would have taken a larger step, but we're forcing it to limit it to that point. Right? So you're going to start seeing this. The problem is going to have a lot of nodes in places where things are happening quickly, and then not a lot of nodes where it just doesn't need it. Right? It just doesn't care. So that's one argument. Let's see, some other things you might want to do. You could change the tolerances. So if I wanted to change my absolute tolerance to something tighter than the default, I could do that with this. If I wanted to change the method that's being used to solve, I could do that. If you look at this, though, RK45, right? So RK45 is actually Runge-Kutta 4.5. So it is a version of the Runge-Kutta technique. You can look at the documentation on that. But it's similar to this. It's just that there's a slight difference for this integration technique. But you can do this. You can do other methods. Yeah, again, I guess I'd look at the documentation on that. Let's see, where do I want to do this? Oh, and then the last thing you can do is, let's say we want to get back an array of temperatures at specific times that we decide what the time is. So we don't want to get back that really short initial time step. We want to just specify what the time is. You can do that by creating this time eval vector and then passing that in. So here I would say, I'm going to make a time eval vector. It'll do the integration, move forward, develop the model. After it's developed the model, then it'll go back with the existing function and just evaluate that function at these time steps. Right? So this is not how it's actually integrating. It's just going back and evaluating at these time steps. OK, so let's look at this. There. So you see now really accurate solution. Again, it's only doing the solution based on my min step, which was 11. But now it's evaluating it at even increments. So that original really compact step is no more. It's still internal, but it's not showing up in our represented solution here. So ultimately, I think when it comes to using this stuff, I'd say you're probably in practice most likely to use something like this because it's such a flexible technique. All you need to do is come up with a state equation. This is probably what you would do in practice. But if you have certain circumstances or this doesn't work, you might go back and use something, one of the other techniques. But I think it's really good to understand where they come from, at least.